So let's look at the solutions to a few in-class questions for lecture 7 and lecture 8. First of all is this build time for vector scan-based stereolithography. So we have a few known conditions, such as this laser scan speed, Vs. Um, and also there's another known value is the width of the cure trace. And the layer thickness is LT. The overall volume of the building material is this volume P, uh, cubic millimeter. Also, the part height H is known as well. As we mentioned in the calculation, besides the laser scanning time, we also need to count this uh, spreading rising time. And each of the spreading rising for the layer is TS. So with all this known, we could compute the overall time for um, print or part. So first of all, we need to compute the volume scan rate. As we know, the linear scan velocity is Vs. Also, it has a width Wt. Then we will have Vs times Wt, and that's the um, area scan rate. And then we have the layer thickness Lt, and combine the three terms together, we will have a volumetric volume scan rate. And that is for I mean, with this known, we could use the overall volume of the material and to divide this overall material by the rate, such that it gives you the laser scan time. That's the time for the laser scanning. And then we could compute the number of layers by dividing the overall height by this layer thickness. Then we have the number of layers. And we also know for each layer, it takes TS for spreading the resin. Then we could time this TS with this total layer number. And after we have the time for laser scanning and also time for the spreading resin, and it turns out we will have the overall printing time. That's how you compute the overall printing time for the laser scanning based stereolithography. Um, so another question in the digital light processing process. Basically, in the digital light processing, we are projecting an image onto the building or building tank, right? So the I mean, the pixel number of an image is known, is fixed. For example, we have an image resolution which is 1920 by 1080, right? This is fixed throughout the whole computation. And we also know the distance from the lens to the projection plane, which is the surface of the resin in the tank. And this distance is 40 millimeter. Then you could compute the smallest feature of the printer can print in both X and Y directions. So how to do that? Basically, you need some trigonometries. As you can see here, you have a view angle 26 in the x-axis and another angle 18 in the y-axis. And you could have a triangle like this, like I draw here. and this one is 40, 40 millimeter. And this angle is the half of 26, so that is 13 degrees. And basically, you want to compute the length of this edge. So basically, you need to use the tangent of this angle times this 40. Then you have half of the image um, dimension in the x-axis. So that is for the whole dimension, you need to multiply it by 2, and eventually you have the dimension in the x direction. So similarly, you can do the same calculation in the y direction, but this time the angle is 18 divided by 2, and still this distance is 40, and you have the length here using the tangent, right? By doing so, you will have both the dimension in x and y. That's the actual millimeter of the projected image. But um, uh, how to compute the minimum printed feature size? Then you need to uh, use the actual image size and divide it by the pixel numbers of the image. So in that sense, you have the dimension in x, and you have the pixel number in x, and you divide the actual image dimension in x by the pixel number in x. Then you have a resolution, which is the pixel, I mean the millimeter per pixel. Similarly, you can apply it to the y direction and got another uh, resolution in y. So um, then you will have this minimal feature size. So that's how you could predict the theoretical minimal 3D printing feature size by knowing those information and do the calculation. Sometimes there could be questions. Basically, you have no idea of this um, distance between the lens to the projection plane. And what you know is the angles, also the, um, let me see. No, actually, you don't know the angles. I'm sorry. Basically, you don't know the angles, but you know the distance, right? So what you could do is, let's say you've already know the distance, but you have no idea about the angles. And another thing you know is you know the dimensions of the image. Um, what you could do is you could compute the angles from this distance uh, of the lens to the projection plane, and also the dimensions in x and y axis of the projected image. Basically, you just do the inverse calculation like what we did here, and use the tangent function. You could have the angles. I mean the angle numbers. So that is similar. That is related to the question um, in our homework. So now you know how to do it. So for the third question, we have this laser exposure in Ryzen, and we have this energy intensity function over here. Basically, this function has two variables, the y, which is the distance of any point in this region um, to the center line of the um, laser beam, and also the y direction indicates the, I mean the z direction indicates the depths of inside the resin surface. And so basically we have all this information known: the laser power, the Gaussian half width of the beam, velocity of the beam, penetration depth, and also the critical exposure level needed to initiate the curing. So this EC is also known. It it is related to the material property, the um, photo uh, photopolymer, the property of photopolymers. And with these known, what is the width of the cured line at the surface? Well, how could we compute it? So you have to understand that at this point, which is the two extreme points of this curve, basically at these 2 points, the energy intensity will be this EC. That means beyond this 2 points, there won't be any material be cured. And right on at these 2 points, you have the critical exposure energy. And so how we use this equation to do the computation? First of all, if we have 2 points here, if we talk about 2 points here, basically the z value will be 0, right? But we don't know the y, and but we know what is the critical exposure energy, and we just substitute this y0 to this equation, and it turns out we will only have this term left, and we could further uh, convert it to something like this, and it turns out you have your y computed. And the y is only basically gives you the width from here to here, from the center to here. For the whole width, you need to double it. And so the solution for the width of the cured line and the surface is something like this. Okay.